Right off the bat, consider a few everyday things. How exactly does Google Maps instantly calculate the absolute fastest route across a jam-packed city? Or think about Instagram. How does it seem to magically know exactly who you should follow next? Well, it's definitely not magic, and it's for sure not random guessing. It's the exact mathematics of graphs. You can think of graphs as the invisible web connecting our entire modern digital life.
Get the difference between a simple graph and a multigraph. A simple graph is as basic as it gets. No loops, no multiple edges between points. Just one clean line from point A to point B. But a multigraph, that's a bit different. It can have more than one edge between the exact same two nodes. Imagine city A and city B again. In a simple graph, there's just one conceptual connection between them. But in a multigraph, you could draw two completely different roads connecting those exact same two cities.
Okay, so every graph boils down to two main things: vertices and edges. A vertex, or a node as you'll often hear it called, is simply a point on the graph. Think of a vertex as a specific city on a map or a specific person on your phone. If we have a group of them, we might mathematically write our vertices as V equals A, B, and C. Then you have the edge. An edge is just the line connecting two nodes together. It's the physical road between those two cities, or the established friendship between those two people. So if point A is connected to point B, we'd mathematically write that edge as E equals A, comma, B. Dots and lines. Vertices and edges. That is your absolute foundation.
So the takeaway here is that we can adapt the graph to fit whatever reality we're modeling. Let's quickly hit two more important variations. First, the pseudograph. This one's pretty unique because it contains what we call loops. That's an edge that starts at a node, goes out, and circles right back to return to the exact same starting node. Second, and this is a real game changer in computer science, is the weighted graph. In this model, every single edge has a specific numeric value attached to it. It's not just a connection anymore, it's a connection with a cost. This could be the physical distance in miles between cities, or even the financial cost of traveling between them. Having that specific data is absolutely crucial for solving massive logistical problems.
Well, computers obviously don't have eyes to look at a drawing of lines and dots, right? So they use data structures. One of the main ways they do this is through an adjacency matrix. Imagine a grid. Along the top and down the left side, we have our vertices, A, B, and C. This gives us a neat little 3x3 grid. Inside that grid, the computer uses simple binary code, just zeros and ones. A 1 means there is a direct edge connecting those two nodes. A 0 means there's absolutely no connection. So, if the computer checks where row A and column B intersect and there's a 1 sitting there, it instantly knows, boom, node A and node B are connected. It's an incredibly fast, efficient way for a machine to map a network mathematically.
Alternatively, computers can use what's called an adjacency list. Think of this more like a relationship roster. Instead of building a giant grid of zeros and ones, the computer just keeps a running list for every single node, explicitly stating who it's connected to. So the list just says, node A connects to B and C, node B connects to A and C, node C connects to A and B. It achieves the exact same goal as the matrix, but depending on how packed or sparse the connections are, one method might actually save the computer a ton more memory than the other.
This right here is why learning this stuff matters so much. Graphs aren't just abstract math. They are quite literally the engine running our modern world. When social media platforms suggest a new friend for you, they are crunching massive undirected and directed graphs to analyze your circles. When Google Maps calculates the fastest route home, it's running intense algorithms over a giant weighted graph, where the nodes are intersections, the edges are roads, and the weights are live traffic times. Your home Wi-Fi, global computer networks, they all use graphs to track connections between devices. Massive transport systems use them to organize crazy complex bus, plane, and train schedules, just to prevent delays and collisions. You're interacting with the mathematics of graphs literally every single day.
Let's actively think about this one for a second. We have a graph with 4 vertices, A, B, C, and D, and we have exactly 3 edges connecting them. There's an edge between A and B, an edge between A and C, and an edge between B and D. So I want you to calculate the degree of each of those 4 vertices. Remember, the degree is just the total number of edges connected to a specific point. Try to picture the lines connecting the letters in your head. I'll give you just a second to figure it out.
Okay, let's reveal the first part of the answer. For both vertex A and vertex B, the degree is exactly 2. Why? Well, vertex A touches 2 edges, the one going to B and the one going to C. Vertex B also touches 2 edges, the one coming from A and the one going over to D. And for the final part of our solution, vertex C and vertex D each have a degree of 1. Vertex C only connects back to A, and vertex D only connects back to B. If you got that right, congratulations, you now officially know how to mathematically analyze the connections within a graph model.